All right. So we have the quadratic equation. This is ax squared plus bx plus c equals 0 means that x is negative b plus or minus root b squared minus 4ac all divided by 2a. The main difficulty is this part here. We're taking a square root of this thing here, b squared minus 4ac. And what this and square roots don't always work, or at least don't always give you real answers, real number answers, for well, if it's given a negative input. So we call this thing b squared minus 4ac. We call it the discriminant because it discriminates between the kinds of solutions you get. If b squared minus 4ac is positive, then this is just the square root. It's a real number. So there'll be two real roots. So if you graph the y equals ax squared plus bx plus c, get a parabola that meets the x-axis in two spots. If b squared minus 4ac equals 0, then the square root of 0 is 0, and these two different roots collapse to 1. So you get one double root. So it's like a parabola that grazes the x-axis. It's as if these two roots here approached each other and became 1. If b squared minus 4ac is less than 0, you have a square root of a negative, which is not a real number, it's a complex number. So you get two complex roots and no real roots. That's like when you graph the parabola and it lifts off the x-axis entirely and meets it nowhere. Well, it lifts off the real x-axis and meets it nowhere. And furthermore, if b squared minus 4ac is a square of something, then you get rational roots. If it's not a square, then you get irrational roots. So, for example, what kind of roots for these equations? 4x squared minus 4x plus 1. They're not asking what the roots are. They just want to know what kinds they are. Well, the discriminant is b squared minus 4ac, negative 4 squared minus 4 times 1, which equals 0. So it's a single repeated root. In fact, a single rational repeated root. 5x squared plus x plus 2 equals 0. Well, d is 1 squared minus 4 times 5 times 2, which is negative 39. So this is not only a negative, it's also not a square. So you get two irrational and complex roots. X times 2x minus 3 equals 20. All we have to expand it and transpose. Get 2x squared minus 3x minus 20 equals 0. Then the discriminant is b squared negative 3 squared minus 4 times 2 times negative 20. After a bit of churning, it's 169, which is a square of 13. So, which is positive and a square. So there's two real roots and they're rational. Two rational real roots. 3x squared minus 10 is 0. Well, discriminant, b is 0, a is 3, c is negative 10. The discriminant is 0 squared minus 4 times 3 times negative 10, which is 120, which is positive, but not a square. So you have two irrational real roots. Enough of that. Next part of this section is that some equations are basically quadratics in disguise. For example, x to the fourth plus 19x squared plus 18 equals 0. Now technically, it's a equation of degree 4, and those can be a major pain. There are formulas for quadratics. There's a formula for the cubic. There is a formula for the quartic, but I've seen it once and only once, and it covered up everything. It was printed on a poster that fits on a wall in fine print. It's just a mess. So I don't know if anybody actually in practice uses the quartic equation. And the cubic equation, it exists. I haven't really seen people use it that often, actually. What else? Oh, yes. And furthermore, there does not exist a general quintic equation. Turn formula, it turns out. Okay, anyhow. So this, however, it looks like a quartic, but really it's a quadratic in disguise because this x to the fourth is the square of x squared. The x squared is just what it is. So you can think of it as x squared squared plus 19x squared plus 18 equals 0. Now this factors into x squared plus 18 times x squared minus plus 1. That equals 0. And now, okay, it's solvable by by the zero factors rule. Either x squared plus 18 is 0 or x squared plus 1 is 0. So either x squared is negative 18 or x squared equals negative 1. Taking square roots, you get x is plus or minus I times 3 root 2, because that's the square root of negative 18. Or x equals I, or negative I, because those are the square roots of negative 1. I 3 root 2, negative I 3 root 2, or I, or negative I. This is also a quadratic in disguise. 2x minus root x equals 3. Transpose the 3. 2x, which is root x squared, minus 1 root x minus 3 equals 0. This is a quadratic for root x. We can solve for root x using the quadratic formula. Minus b plus or minus b squared minus 4 times a times c. Okay, minus negative 1 is 1 over 2 times 2, which is 4. This comes out to be 25. So 1 plus or minus root 25 over 4. So root x, mind you, is 1 plus or minus 5 over 4. Oh. Ooh. East. Oh my God. Oh my God. I made a dreadful error. I should honk myself. 1 plus 5 over 4 is 6/4, which is 3 halves. 1 minus 5 over 4 is negative 1. Ooh, dear. Just a moment. Let me write that down. I shall have to fix it in the canvas. Root x equals negative 1. Well, already we should see that roots are never negative, so this doesn't work. But so either, since root x is 6/4, and we throw out negative 1, then x is the square of 6/4, which is the square of 3 halves, which is 9/4. And okay, here I'm mistaken that x equals 1, but if you check it out, it doesn't work. So the solution is x is 9/4. 2 times 2x plus 1 squared minus 7 times 2x plus 1 plus 6 equals 0. Now we could solve this by expanding this and turn until we get a quadratic and solve that way. But this is actually a quadratic in 2x plus 1. So we can solve first for 2x plus 1. B is negative 7, which goes here and here. A is 2, which goes here and here. C is 6, which goes here. Minus negative 7 is 7, plus or minus root of this monstrosity, which turns out to be 1, all over 4. Root 1 is 1. 7 plus 1 over 4 is 8/4. 7 minus 1 over 4 is 6/4. That's 2 or 3 halves. So all right, 2x plus 1 is 2 or 3 halves. You subtract 1 from both sides and divide both sides by 2. You get either x equals 2 minus 1 over 2, or x is 3 halves minus 1 over 2. And after a little bit of fraction arithmetic, you get x is a half or x is a quarter. And both solutions work. All right, so some examples. One example. One, what do they call them? Look-alike problems. Y to the 2/3 plus y to the 1/3 minus 20 equals 0. Now this is the square of y to the third. This is y to the third. You treat it as a factoring problem. And this factors into y to the third plus 5 times y to the third minus 4. It's because 5y to the third minus 4y to the third is y to the third. Y to the third times y to the third is y to the 2/3, and 5 times negative 4 is negative 20. So we factored it, and one of these factors must be 0. So either y to the third plus 5 is 0, or y to the third minus 4 is 0. This being 0 makes y to the third is negative 5. This being 0 makes y to the third is 4. Then we cube both sides, so y is negative 5 to the third, or y equals 4 to the third. That comes out to y equals negative 125, or y equals 64. Here's a very similar problem. Instead of 2/3, 1/3, and minus 20, it's y to the negative 2 plus y to the negative 4 minus 1 minus 20 equals 4. Now this factor is pretty much the same way. Instead of with y to the third power, it's y to the negative 1 power. Y to the negative 1 plus 5 times y to the negative 1 minus 4 equals 0. And again, this factors this way because y to the negative 1 times y to the negative 1 is negative 2. 5y to the negative 1 minus 4y to the negative 1 is y to the negative 1. And 5 times negative 4 is negative 20. So y to the negative 1 plus 5 times y to the negative 1 minus 4 equals 0. One of these factors must be 0. If this is 0, then y to the negative 1 is negative 5. If this is 0, then y to the negative 1 is 4. So the reciprocal is one of these two things. If you take reciprocal of both sides, you get y equals negative 5 to the negative 1 or 4 to the negative 1. Or in other words, y is negative 1/5 or y is 1/4. And that concludes this section.